Hello and welcome to our presentation for Assignment 2, Predicting Steam Reviews from Text Data. So what is a Steam review? Well, Steam is an application that allows users to buy and install games, and these users are also able to leave reviews of the games on their store page. A review typically consists of whether or not a user recommends or does not recommend the game, as well as some supplementary review text for why they made that decision. Our goal will be to predict if a Steam review is recommended or not recommended based on that review text. So, after we create our model, we're going to be evaluating it by computing the test accuracy for both our model and the baseline model and comparing them. And we're going to do that by conducting a simple 80-20 train test split and evaluating our test accuracy for each model. So how does our model actually work? Well, the simple process is first, we're going to extract each review text and tokenize them into unigrams, bigrams, and trigrams, and more on that later. We're going to take these tokens and convert them into TF-IDF features, and with these TF-IDF features, we can train a linear logistic regression classifier to help us make predictions. This is different from our baseline model for two main reasons. Our baseline model will simply utilize unigrams instead of the three n-grams, and it's also going to be constructing a bag of words feature vector instead of TF-IDFs. And so it'll train the same logistic regression classifier just with those different features. And this is actually the same model that we created in homework 3.
Now let's talk about our dataset. Our dataset consists of reviews from Steam's best-selling games for February 2019, sourced from Kaggle. Now within our dataset, it contains 434,000 reviews, and within these 8 attributes, we focused on review, the text of the user review, and the y-axis being recommendation, whether or not the reviewer recommends the game. Now looking at the distribution of recommendation types, we can see that 70% are recommended while 30% are not recommended. This is likely due to players who buy the game would likely be more inclined to give a positive feedback rather than giving a negative feedback on a game they bought. Now looking into pre-processing data, we decided we wanted to make a test function in order to test whether we should include lemmonization, n-gram types, or stop word removal. The way this function works is using a regex tokenizer to remove non-English and punctuation, and then taking in parameters to decide whether we should remove stop words, if we should do stemming, or if we use bigrams or unigrams. This carries over to our next functions, which use tokenizer values to create lists of the most common n-grams. In each function, they take in review tokens and create their corresponding lists of n-grams through this double for loops. From these for loops, we can sort the dictionary to then return the most common n-grams. This leads to a matplotlib bar chart. Within this bar chart, we can see that the unigrams showcase a lot more neutral and positive words. We can see game and games, and we can see that game occurs almost 400,000 more times than second most in the dataset due to being Steam. Now, we should also try looking further into n-grams to see if any non-neutral key phrases stick out. So looking into bigrams and trigrams, we can see that bigrams has a lot of positive words. We can see good game, great game, fun game, love game, types like that. And then in trigrams, we can see also some positive. We can see yes, yes, yes. We can see 10, 10 would. And then we can also see some negatives. We can see cheaters, 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 lag, lag, lag. But what if we also focused on the y-axis? What if we start looking into recommended and not recommended? In this case, we can't look at unigrams due to the frequency and neutral words. So we'll take a look at bigrams. We then look at this, and we can see that on the left side with recommended bigrams, we can see that that there's a lot of positive words. We can see 10 wood, gameplay. You can't see that much negative words. But in not recommended bigrams, surprisingly, you can see some positive words. You can see buy game, play game. You could see single player and receive free, some like neutral words. We could also still see some negative words, such as don't buy and stuff.
Now that we've done our EDA, let's start building our model. So our model takes in review text and it simply predicts if a review is recommended or not recommended. So a lot of models can probably do this as well, but we decided to use logistic regression, mostly because we can actually code it from scratch, and it would also provide some results that are really simple to understand and they're interpretable. So yes, we are trying to solve an ML problem. This is because our problem is mostly a binary classification one, where we're trying to predict if a review is recommended or not recommended based on text data. And we're solving it using supervised learning since we're training it on a labeled dataset. So what our model will actually do is it'll optimize a loss function. So first, it makes predictions using this sigmoid function, and then it will compare it to the actual values to get the loss. So the value of these predictions are dependent on this linear score. And the linear score is calculated by multiplying a word's TF-IDF value with the feature weight of the word for every word in the review vector. And then the model will adjust the feature weights to make the overall loss as small as possible. This is actually mostly going to happen behind the scenes since we're going to be using sklearn's logistic regression function. So what is TF-IDF, since we've talked about it so much? Well, TF-IDF simply captures how important a word is in our dataset. So a word with high TF-IDF value would be very informative, and a word with a low TF-IDF value would be not as informative. But how exactly do we calculate this? Well, now we need to talk about the TFs, which are the term frequencies. So this is simply how much does a term appear in a document. And we calculate this by dividing the number of times a term appears by the total number of terms in the document. And we're going to need to calculate this for each word in each document. The IDFs, or inverse document frequencies, is a measure of how rare a term is across all documents. To calculate this, first we'll need to calculate the document frequencies, which is simply just the number of documents that contain that specific term. And then we're going to apply an IDF function to it, which will convert the document frequency into a weight. And this weight essentially shrinks the influence of common words. Well, we talked about how we calculate TF-IDFs for words, but we're actually not just using words, we're using n-grams, specifically unigrams, bigrams, and trigrams. A unigram is just a singular word, but a bigram is a sequence of 2 consecutive words, and a trigram will be 3 consecutive words. So our model will not just be making predictions based on unigrams, it will also be using bigrams and trigrams. Now let's begin talking about our code that we actually wrote to train our model. So first, this is function create n-grams. So this function takes in review text as an input, and then it splits that text up, removes punctuation, and then this gives us a list of just the words. Then it loops through all the words for a few times, and it constructs n-grams from size 1 to n, where n is the specified size. For example, if we were to call create n-grams on a sentence, this game is so good with n-grams of 3, it'll output a list of tokens where the tokens are all the unigrams, bigrams, and trigrams. Next, we wrote a function to calculate the term frequencies, and this is simply a function that takes in the tokens, which in our case will be a list of n-grams, and then returns the term frequencies for each n-gram if they're actually an n-gram that we care about. We also wrote a function to calculate the document frequencies, and what this function does is it loops through the entire dataset, tokenizes each review into n-grams, and then it counts the number of documents that contain that n-gram. Now that we have the TFs and DFs, we can create our TF-IDF function, which is responsible for creating a matrix of the TF-IDF vectors. This function works by looping through the entire dataset and calculating the term frequency for each review. Then using these term frequencies, we're able to create TF-IDF vectors for each review by multiplying the term frequency and IDF of each word in that review, and we do this for every single review. After that, we're able to append these vectors to our overall matrix and return the overall TF-IDF matrix. But before we do that, we do normalize our vectors. And this is because in longer reviews, they often contain more words, and so if we don't normalize them, many words in these longer reviews will be given a higher term frequency, which can cause bias. Finally, we can start creating the code to actually build our model. So first, we'll define our hyperparameters. NW and n-grams are our 2 hyperparameters. NW essentially tells us the top NW common words that we're going to look at and use for our model. N-grams is the largest n-gram size that we're going to be using as well. and in our case it's 3 because we're going to be using unigrams, bigrams, and trigrams. Next, we're going to process our data by filtering out reviews that have no English characters, and this is just a quick and easy way to get rid of most of the non-English reviews. Afterwards, we'll create our train and test sets, and we do this by taking the first 80% of our data, and that'll be our train set, and then the rest of the 20% will be our test set. Next, we'll create gram counts, and these counts basically tell us the count of each n-gram in our entire train data, and we simply do this by looping through our data and essentially counting the number of times we see each gram. And we do this because we want to create gram set, which essentially will only include the top NW words that we want to look at. The reason we actually do this is because if we have many words that we're going to be looking at, then our model will be very difficult to train. It'll be very time consuming. So by only looking at the top NW words, we'll speed up our training. We'll then create our IDF's dictionary. So how we do this is we calculate the document frequency first using our method, and then we apply the IDF formula to calculate the IDF of each word. Finally, we're able to use this TF-IDF function, since we have all the necessary items, to create a matrix for both the train and test data. This matrix is then used to train our logistic regression model, and we're using sklearn's built-in function for this. Now that we have our model, we can start making predictions. So the test accuracy of the model that we just trained is around 85.6%. So why is this model good for us? Well, first, we're using TF-IDFs, which lets us focus on most of the important words, specifically the words that are frequent in a specific review but rare across the entire data set. So they give us a lot of information about a specific review. We also included an approach where we used n-grams, and this further improves our model because phrases like not good would be captured better. In a unigram model, not and good would be separate, and so of a review that contains not good might be assigned positive sentiment because it sees good. Some disadvantages I ran into mostly were that when we trained our model using our implementation, which was from scratch, it was quite slow because there's many loops and Python doesn't handle that very well. So to mitigate that, we can actually use sklearn's built-in TF-IDF vectorizer, which is way faster. Essentially, all we need to do is feed in the reviews, and it'll pretty much do the same thing as what we just coded. The accuracy of this sklearn's TF-IDF vectorizer using the same hyperparameters showed a really similar accuracy, which was only different by about 0.1%. That's likely due to just random noise and due to the fact that sklearn might be using a different loss function. But specifically, this is way faster because sklearn uses optimized C++ to run things behind the scenes. So we were even able to increase our NW to 10,000 instead of 1,500, and we saw a much higher accuracy score. It increased by around 2%. So now that we've got our model, how good is it? So again, to reiterate, to evaluate our model, we're going to be comparing our model's test accuracy compared to the baseline model's test accuracy. So let's briefly go over the code for the baseline model, which is the same as in homework 3. So first, we have this feature cat function, and basically all it does is it creates a single bag of words feature vector for a single review. And it does this by simply looping through the words in that review and counting the times it sees a word. We'll then use the previous function to inside this new features function to construct a full feature matrix by getting the feature vector from each review. Now, to train our baseline model, we're going to be using a very similar process to what we did, but essentially the main difference is that instead of getting the n-gram counts, we're going to be using word counts, and that's what's being used in the words and word set. And the same logistic regression model is going to be used, except we're just going to be using the bag of words matrix instead of TF-IDF. So how well does this do? Again, we calculated the test accuracy of our model earlier, and test accuracy is probably the best metric that we can use for evaluation because since it's very simple and the direct way of evaluating things, and our train test split is the same for both our model and baseline model. Test accuracy directly tells us if one model is doing better than the other. So our model had an accuracy of 85.6%, which is around 0.5% better than the baseline accuracy. And so this probably means that our model is slightly better, but the baseline model was quite good already. Increasing the number of words did show a higher accuracy for our model, so with enough computational power and a high enough NW, we can get even better. To finish our analysis, let's take a look at which words our model thought were to be very important. And so this code simply takes the top 20 positive and negative features from the model, and we're going to be plotting them. So let's take a look. We see that for the negative sentiments, there's many words that we do expect to see, such as refund, unplayable, waste, trash. And for positive sentiments, we do see some words and phrases that we expect to see there, such as addicting, perfect, awesome. But strangely enough, we do see soccer and football. And what this probably means is that players on Steam typically just enjoy playing games with soccer or football in them.
All right, now that we explained our model, here are some inspirations we got from research papers and notebooks from Steam reviews. The first research paper that we use in consideration when tackling this assignment was a modernized approach to sentiment analysis of product reviews using ByGru and RNN-based deep learning models. This paper goes into detail on the backgrounds of using and tackling the levels of sentiment analysis, but primarily sentence level, which was the same style of our dataset. They utilize natural language processing and deep learning techniques to tackle developing binding online product reviews. Looking at this image right here, we can look at their process within their product review analysis system. We can see that they're pre-processing stop word removal part of speech tagging. We can see their feature extraction that we'll later talk about. And we can also see what exactly they're trying to compare and what they're trying to tackle. Now, of the several models they discuss, RNNs with LSTMs were the main ones they use. Recurrent neural networks with long short-term memory. RNN, a neural network that processes data one at a time, which basically means that it has a memory of what comes before, making it perfect for set-level analysis. However, as the sequences increase, the earlier info gets forgotten. This leads to its improved version, LSTM. This uses gate-like ideas that decide whether key features would be useful to keep and what words are unnecessary that can be thrown out, assisting in RNN's primary issue. In order to extract the feature, they would use bidirectional gated recurrent units, ByGru. Now, two gated recurrent units, GRU, that would each consist of 3 blocks that function similar to RNN, which would decide to forget or keep past info. ByGru would use these GRUs to have one read forward while the other reads backward to help understand the context for words from both sides. Now, using the combination of these three, it significantly boosts their standard evaluation metrics, as we can see from the high 90s on the performance analysis. Now, if we look at the right, we can see that it outperforms most of the other neural networks, such as 94.7% on MLP and crushing deep convolutional neural networks. However, why didn't we use recurrent neural networks? The main reason is computational power. RNNs require large computational power to tackle, something that we lacked. We could have cut a chunk of the data and used that small chunk to run a basic version of the model, but that would be very ungeneralizable due to the lack of data and wouldn't really work with the rest of the data we had. Now, for our second research paper, we decided to focus on TF-IDFs and Word2Vec, looking into comparative analysis of TF-IDF and Word2Vec in sentiment analysis, a case of food reviews. Now, Word2Vec is used for word embedding and discovering semantic levels, similar to TF-IDF. Using 560,000 food review data, this paper focuses on comparing the accuracy of the two between different data sets. Now, one thing that we can notice within this bar graph is that the training data for TF-IDF is high due to overfitting, leading to 73.9% test accuracy. However, Word2Vec has a balanced accuracy on both sides, with 68.6%, showcasing its generalizability. We can see this even more when looking at the graph with different dataset sizes. With the 10K, we can see that it stays around the 65. With the 50K, we can see that it stays around like the 72%. However, As we look at it, we can see that although the training accuracy for TF-IDF is really overfitted, we can still see that TF-IDF is generally performing much better, which is why we rather would choose a stronger model than have something that would be more generalizable. Looking into notebooks using the same datasets, we found Pavlov's approach using BERT. Within their preprocess, they decided to ditch data cleaning and reduce the values to deal with computational power. This went from 400,000 datasets to points to 25,000. Here we can see them setting up BERT through TensorFlow and Keras. BERT is known as bidirectional encoder representations from transformers, an NLP model that reads from left to right and right to left, rather than other NLP models going from left to right. Using transformers and encoding, it allows us to see every word in the sentence to look at every other word. We can see them tokenizing the text leading into BERT encoding. Here in BERT encoding, when tokenizing the text, there are special end tokens that are necessary for BERT to work. CLS and SCP are both used at the end to help the model check for where the text ends. Towards the later half of the code, we can see them tokenizing the data to build a classifier. He builds a classifier using the encoding values and takes the embeddings for all the tokens to use for binary classification. This is then compiled, leading to training and testing for the model. From here, we can see the final results of the BERT model getting 87.6% accuracy. It was a very strong model, however, it lost a lot of accuracy due to the lack of data and data cleaning. This was due to the limitations in computational power, and are things that we try to avoid for our model. However, they provide us with a good understanding on what to avoid and what to use within our own model. As such, we chose TF-IDF since it would help mitigate these problems. Thank you.